we've already learned how to explain the motion of a moving particle, and we did that a couple ways, but the first way we did it was in terms of Newton's second law. So here we have the net force caused the acceleration. So what we want to know is what kinds of things cause rigid bodies to rotate. In particular, if you think about a particle, it was the net force alone which determined how it would move. If you applied a certain amount of force, the object would accelerate in a certain way. So if you pushed it, for example, with a given force, it would take a certain amount of time to move a given distance. And if you exerted the force in a different direction, it would go in a different direction, but it would still take the same time to travel a certain distance if it was starting from rest. So what we want to know today is what kinds of things would affect how an object would rotate, in particular, how long it would take to rotate a certain distance. So here we have a door, if you like, and we're going to apply a force to the door. So here is the force that we're going to apply to the door. This is the way you would ordinarily push a door. And so if I start the simulation, you can see it takes about 2 seconds for the door to rotate 90 degrees. So the question is, what if we applied a different force? For example, what if the force were smaller? So let's make the force smaller. So with the force smaller, if we try again, no big surprise, it takes longer for the door to rotate the same 90 degrees. It took almost 3 seconds in this case. If we made the force bigger, then you might guess it would take less time to rotate. And sure enough, it takes a little less than 2 seconds to rotate all the way to 90 degrees. So that's not a big surprise. The more force you apply, the more the door will rotate, and the less force you apply, the less it will rotate. But what if we applied the same force? Let's go back to the original force. But what if we moved the force and applied it in a different location, say there, or even here? What if we applied the force in that location? Same force, same door, but do we get the same effect? As you can guess again, you've pushed doors before. That's not nearly as good a way to push a door. Even though we applied the same force, same direction, same door, but by applying it in a different place, now it takes almost 4 seconds for the door to rotate 90 degrees. So as you can see, with rotating objects, just knowing the force is not enough. Now, there's one other thing we can change. Let's move the force back to the edge of the door. What if we pushed in a different direction? For example, what if we pushed in this direction? So now we're applying the same force in the same place even, but now we're applying it in a different direction. So what do you think? Is the door going to rotate more or less easily? Well, as you can see, the door rotates much less easily. It takes almost 3 seconds for the door to rotate all the way to 90 degrees. Now, if we really wanted to be extreme, what if we tried something along these lines? Again, this is the same force. It's being applied in the same place, but it's being applied in a different direction. Now, if we run the simulation, you can watch the clock is running, but the door isn't rotating at all. So in this case, even though we pushed on the door, same place, same amount of force, we got absolutely no effect on how it would rotate. So when it comes to explaining the rotation of a rigid body, clearly the force alone is not going to be enough. The force is important, but how we applied the force, where we applied it, the direction we applied it, those were important things as well, not just the size of the force. And so we're going to need to come up with a new concept that includes all three of those things: the size of the force, where the force is applied, and the direction of the force. That new topic, or that new quantity, we're going to call torque. So torque is going to be the rotational version of force. And we want to define it in such a way that the more torque we apply, the greater the rotational motion will change, just like we saw in the simulation. So here's how we're going to define the torque. We're going to define the torque to be the magnitude of the force times something called the lever arm, we could write it like this, where F stands for force, the R with the little perpendicular symbol stands for lever arm, and that funny looking letter on the left side is the Greek letter tau, which is the traditional symbol for torque. So we have the torque is equal to the force times the lever arm. So the lever arm is the perpendicular distance from the axis of rotation to something called the line of action. So to help you understand what all that means, let's take a look here at the bottom of the page. Let's take a look at the normal way you would push a door. This is the first way we did it in the simulation. So the line of action is the line along which the force is being applied. So we're pushing at the edge of the door, perpendicular to the door, and so that's what the line of action shows. It's perpendicular to the door and passes right through the end. So the line of action is the line along which the force is pushing or pulling. So the lever arm is then the distance from the axis to that line, and it's the perpendicular distance. In other words, it has to be measured along a perpendicular. That gives us the closest or the shortest distance from the axis to that line. So in this case, the door is perpendicular to the line of action, so the lever arm would just be the width of the door in this case. So we measure along a perpendicular from the axis to the line of action. Here's another way you could push a door. We tried this in the simulation as well. If we find the line of action, there would be the line of action. And now to find the lever arm, we have to measure the perpendicular distance from the axis to that line. So we need to make a new line perpendicular to the line of action that goes to the axis. And that's where we would measure the lever arm. Again, it's the shortest distance from the axis to the line of action. It's measured along a perpendicular. So notice that it's not necessarily the distance from the axis to where the force is actually applied. It's the distance from the axis to the line of action. So where the force is applied is not so much the issue as along what line is it being applied. And you can see in this case the lever arm is shorter than it was in the first case, and just like we saw in the simulation, the torque ought to be smaller as well, because this is a less effective way to push the door. The same force times this shorter lever arm would give us a smaller torque, and again, pushing the door this way isn't as effective. We would get less effect for our efforts. It would take longer for the door to rotate 90 degrees, for example. Here's the last way we tried it in the simulation, and remember, in this case, the door wouldn't even rotate at all. The line of action would look like that, and as you can see, the line of action actually passes right through the axis of rotation. So the lever arm in this case would be 0. The shortest distance from the axis to the line of action is 0, so there's no lever arm in this case. Now torque, just like force, is going to be a vector, and so we need to figure out the direction of the torque, and we're going to define it like this. Whatever direction the object would rotate, if that force acted on it alone, that's the direction that we're going to call the torque. So if you look at the first case we considered, if you push the door in that way, the door would rotate counterclockwise. So we're going to say that torque has a direction that's counterclockwise. In the middle case, if you pushed on the door in that way, the force would cause the door to rotate clockwise. So we're going to say that's a clockwise torque. Now in this class, we're only going to focus on situations where the axis of rotation is fixed. So those are the only two possible directions we can have then about a fixed axis. Either the force would make the object rotate clockwise, and we'll call it a clockwise torque, or the force would tend to make the object rotate counterclockwise, and we'll call it a counterclockwise torque. Now, there may be other forces and other torques, but again, the direction of the torque can be found by pretending that each force is acting alone and the object starts from rest. Just ask yourself, which way would the force make the object rotate? We need units for measuring torque, and so the official unit is something called a Newton meter. There's another common unit that's from the British engineering system, that's the foot-pound, and it turns out those are about the same size. A Newton is a bit smaller than a pound, but a foot is a bit shorter than a meter. So if you multiply those all out, they're really about the same size. A foot-pound is just a little bit bigger than a Newton meter. Now, just like when we were considering forces, there are often more than one force acting on the same object at the same time. The same thing goes for torques. You may have more than one torque acting on the same object at the same time. And so we are going to need to find the net torque. In other words, find all the torques acting on the object of interest and add them together. And that will give you the net torque, the one torque that you could substitute for the actual torques present and actually get the same outcome. So when you go to add up the torques, remember the torques are vectors. In our case, it's very simple. The torques can only be one of two directions, clockwise or counterclockwise. So we could use a plus and a minus to indicate the directions, but we still have to take the directions into account when we add the torques together to get the net torque.